let me first, before I start, thank the organizers for putting together this very interesting conference and also for the opportunity to present my research here. So we all know that charged particles behave in a very unique way to magnetic fields. They perform these circular motions. And you can envision that effect very nicely if you just take an electron beam and send it through a gas chamber, subject it to a magnetic field. And then the collisions of the electrons with the gas atoms will lead to these nice trajectories you can observe. Now, since we're here at condensed matter, of course, I don't want to consider free electron beams, but rather want to consider materials which have electronic degrees of freedom. So this talk is going to be about metals. To be more specific, it's going to be how to probe metals. Now, metals, or the main feature of metals, is this extensive amount of charged low energy degrees of freedom. They form this manifold in the reciprocal space, which you all know is the Brillouin zone. Fermi surface. Well, the Fermi surface determines all thermodynamic and transport properties of your material. It's also crucial, or the details of this Fermi surface are crucial in order to understand all our instabilities from our material. So whether it exhibits superconductivity, magnetism, or any charge density waves. So an essential question which we have to answer if you want to study properties of metals is how can we measure these Fermi surfaces? How can we probe them? Now, in 1930, De Haas and van Alphen took a huge step toward that direction, even though they didn't realize it at this time, by putting a single crystal of bismuth into a magnetic field, and they observed in the magnetization these characteristic oscillations in 1/b. Now, nowadays, we know, of course, that these oscillations are a direct probe of the underlying Landau level structure in our metal. Then in the 1950s, Lifshitz, Kossovich, and Onsager developed really a fully fledged theory. And since then, this measurement of quantum oscillations has evolved into one of the most precise experimental tools to measure Fermi surfaces and other Fermi liquid properties. The nice part is that you can describe the motion of the electrons in a magnetic field simply by semi-classical equations of motion. So if you put in a magnetic field, you can describe your force by the Lorentz force, and the Lorentz force constrains your allowed trajectories on orbits on this Fermi surface. So these electrons are orbiting on the Fermi surface around the Fermi surface, and they are constrained to the intersection of the Fermi surface with a plane which is perpendicular to the magnetic field. Now, in order to do semi-classics, you have to quantize that according to the Bohr-Sommerfeld rule. So you quantize it, and what you will find are exactly your Landau levels, but you can also find the periodicity of these oscillations. So your oscillations are periodic in 1/b, and the frequency of these oscillations is exactly given by the area this orbit encloses in reciprocal space. Now, how can we use that to actually probe properties? So here's a kind of recipe how to do that. So you have some Fermi surface, you apply a magnetic field, you get all your extremal orbits around the Fermi surface. So in this case, it would be the alpha orbit, which goes around the belly, and the beta orbit, which goes around the neck. And these generate, according to Onsager, two frequencies. Then you can measure, for example, conductance or magnetization or whatever you want, and you will observe these oscillations. Well, then you perform a Fourier transformation, where you will see exactly two peaks at the frequencies which correspond to the area of these two orbits. Now, in practice, this spectrum on the right-hand side is a little bit more complicated. So it looks more like this. So there's a large amount of frequencies, and you have to carefully map out which frequency belongs to which Fermi surface sheet in your Brillouin zone. And this can be very complicated. And what I want to propose today is that actually not every frequency you can observe in this spectrum here necessarily corresponds to a Fermi surface, but could also come from a different effect, which is, in our case, a scattering. the mechanism itself is very simple. So what we considered is a metal which has two Fermi surfaces. Take it for now in 2D, but we can extend it to 3D then. Now, additionally to this model with two Fermi surfaces, they can be generated by parabolic bands or Dirac cones or whatever you prefer. We add impurities into our system. Now, we know that the effect of impurities is fairly simple. So they just broaden our bands, they broaden our Landau levels. If you, however, so they give us a finite quasi-particle lifetime. This is the point. Now, if you evaluate it a little bit more carefully, you will see that actually the quasi-particle lifetime is not a constant with respect to the magnetic field, but it will acquire quantum oscillations as well. It's too much. Well, not too much. Okay, perfect. Now, you can either evaluate that diagrammatically, that's what we did, or you can also simply see it from Fermi's golden rule. Fermi's golden rule tells you that the transition rate is proportional to the density of states. And now the density of states here on the right-hand side is just Landau levels. So when you tune your magnetic field, this will oscillate. And so also your transition rate will acquire oscillations. And these are exactly the quantum oscillations which I introduced before. Now, the nature of these impurities is actually crucial. So your impurities can have two different effects on the bands. So there's two types of processes. So one of them is you scatter on a Fermi surface to the same Fermi surface again. So that's an intra-band process in this case. Whereas there's also the beta processes, which allow scattering from one Fermi surface to the other Fermi surface. And these have different effects on these quantum oscillations of the quasi-particle lifetime. So when you look at the lifetime of the first band here, you will see that you get oscillations with the same frequency as this band generates, with an amplitude set by alpha, so by the interband processes, whereas you also get oscillations with the respectively other frequencies, so with the frequency of the other band. And the amplitude of that is set by these interband scattering processes. Now, what I want to calculate is Kubo formula. So if you evaluate, so I want to calculate conductance or conductivity. If you evaluate Kubo formula, you will see that in the end, you end up with an expression which is something like the oscillation with a frequency times its lifetime. Now, as I said, the quasi-particle lifetime is not a constant in our case. It will acquire oscillations. And then it's exactly these cross terms. So the terms cosine of f2 times cosine f of 1, which will generate you new frequencies. So these are like modulations of the original frequencies. And these will give you new frequencies, which are the sum and the difference of the main frequencies. Now, due to the origin, we call them quantum oscillations of the quasi-particle lifetime. You can derive all that analytically. And in the next slide, I want to talk a little bit about the main features of these quantum oscillations of the quasi-particle lifetime. And the first point is they have a very interesting temperature dependence. Now, their like form of the temperature dependence is the same as for basis quantum oscillations. So they also, you can associate effective mass with them, the Lifshitz-like, and the effective mass which you will get is exactly the sum and the difference of the basis effective masses. So this has to be seen in contrast to the known mechanisms where combination frequencies always come with a strong temperature dependence, usually just the product. And there's a very important difference, can lead to a very interesting feature, and that is temperature stability. So if the masses of these two main frequencies are roughly equal, you can see that the difference of those two is roughly 0. And then the difference frequency does not acquire any temperature smearing at all. But when you increase temperature, your main frequencies will go down. However, your difference frequency can remain finite. And even though it's only a modulation of the main frequencies, it can become the dominant part of your spectrum. Now, the third point I want to make is, I guess, the most important point on the slide here, which is that if you look at the difference frequency for two electron orbits, its interpretation is entirely different to the semi-classical theory I introduced in the beginning, because there is no semi-classical orbit which you can draw for the difference frequency. So if you would want to draw an orbit which encloses an area which would correspond to the difference of the main frequencies, it would be this red shaded area in here. Now, let's think about a path which encloses the red shaded area. First, you would need to go around the outer Fermi surface, anti-clockwise, before going around the inner Fermi surface clockwise, this direction. That would enclose the red shaded area. Now you can see if you go around the inner orbit clockwise, you have to go against the direction which is dictated by Lorentz force. So this path is semi-classically forbidden. It's not allowed. You cannot take it in these like metals. So if you think about these difference frequencies, we cannot think about a semi-classical path which induce them, but it's purely a modulation effect coming from the quasi-particle lifetime. The last point, we also computed the de Haas von Alphen effect, and these difference frequencies are absent in the de Haas von Alphen effect. You can imagine that simply by the fact that the density of states does not depend as heavily on the quasi-particle lifetime as the conductance or the conductivity. In the next part of my talk, I want to present several examples where we believe this theory is actually realized in experiment. And I want to start with the topological semimetal, the 3D topological semimetal cobalt silicide. So cobalt silicide has been measured by several groups. They all agree on the main frequencies. It has a very simple quantum oscillation spectrum, and that's also the reason it's a very nice example to study it first. So, but you can basically only see, due to symmetry, there's only 2 allowed orbits around the R point, which will give you quantum oscillation frequencies. So these are the main features in your spectrum. It's alpha and beta frequency. However, if you zoom in and look a little closer into the spectrum, you can see it around 100 Tesla, a frequency which roughly corresponds to the difference of these 2 frequencies. And between the 2 second harmonics, you can see a peak which roughly corresponds to the sum of these 2 frequencies. Now, in order to assess that this is really the difference and the sum of these main frequencies, we looked into the angular dependence. And you can see that alpha and beta have some angular dependence, some dispersive part, which is difference for alpha and for beta. So also the difference frequency will have some angular dependence. And then we just compared our measurements for different angles with our predictions from our measured main frequencies. And you can see it corresponds very nicely here, the calculated frequencies and the measured frequencies within the error margins. So the essential outcome here is that we observe a difference frequency which does not have a semi-classical orbit in a bulk 3D system here. The next part will be the temperature dependence. So we looked into the temperature dependence of these quantum oscillations. Here on the left-hand side, you can see the raw data. There's nothing done with it except that a background is subtracted, which is the usual step. And you can see at low frequency this blue beating pattern here, which always arises when you have 2 close frequencies. Now, these beating patterns here have nodes. And if you go to the raw data at higher frequencies, you can see there's only one slow oscillation which survives these high temperatures. And these slow oscillations has at minima exactly at the nodes of the beating pattern. So this is exactly the difference frequency, which you can see already in the raw data up to 60 Kelvin. Now, if you take a little bit more of a quantitative approach, you can really determine the effective mass of the difference and the sum. And you can see that it nicely corresponds to our theoretical predictions or to our theory. So the difference really comes roughly with the difference of these 2 effective masses, and also is visible far beyond the point where we can observe the main frequencies, and the sum also roughly fits to the sum. Now, the last point, which is to clarify, is I told you need some sort of finite interband coupling between these 2 orbits. What could be the finite interband coupling in cobalt silicide? Well, we have an idea, and this is if you look at the 2 orbits which give you the main frequencies, you can see that the spin density on these 2 orbits is polarized perpendicular to the Fermi surfaces. However, on different Fermi surfaces, they're polarized anti-parallel. So if you assume that your main part from scattering is low momentum scattering, which is a reasonable approximation. You can see that for a scattering process, you need to flip your spin. So you need magnetic impurities, which break time reversal. And therefore, you need these magnetic impurities. And indeed, it has been known that in cobalt silicide since the late 60s, that there are magnetic impurities present if you have some sort of other impurities in your system. Okay, so my theory is quite generic, so I should provide more than one example of it. Now, these difference frequencies are actually already known in tailored 2D systems. So they're known as magneto-inter-subband oscillations, and they emerged kind of like as a special case out of our theory. So that are already known since the late 80s. And in the 2D community, they're also used. So for example, Pablo Herrero, who I think just left, measured this, and there they used the temperature stability of these difference frequencies in twisted bilayer graphene to determine actually the temperature dependence of the quasi-particle lifetime, because you know that the difference frequency should not depend on temperature in this case. However, you can see a temperature dependence which you can associate to like an increase or like a decrease in the quasi-particle lifetime. In this case, the quasi-particle lifetime comes not from impurities, but from electron-electron interactions. However, I want to focus on 3D systems, and there is more examples to 3D systems. So for example, this is the topological semimetal molybdenum silicide. And you can see again, this has two electron orbits, beta 1 and beta 2. You can see in the spectrum, there are two main peaks. If you look at low frequencies, you can see another peak at low frequencies, which roughly corresponds to the difference. It's stable in temperature. It's identified by the authors as the difference of these two main frequencies, and they don't have a clear explanation for that. At least they state this in their paper. This is another example. This is the ferromagnetic Kagome semimetal. It again has two orbits. Now, the difference is here that one orbit is hole-like, the other one is electron-like. So based on our theory, we wouldn't expect to see a difference frequency here, or in other words, the difference frequency would be also generatable by a semi-classical path. However, the sum is not. Nevertheless, here they observe the sum. It's identified by the authors as the sum. It's, again, more stable in temperature than the main frequencies. And again, they don't have a clear explanation for that. Here's a topological semimetal zirconium silicon sulfur. They did two measurements. That's very nice. They did measurements of transport, and they measured the Haas-van-Alphen effect in the upper panel. Now, there's again the alpha and the beta orbit here, which will be the two relevant orbits. One of them is electron, one of them is hole-like. So you wouldn't expect to see a sum. Yet here's the sum. The sum is there in transport. It's identified by the authors as the sum. The sum is, however, absent in the Haas-van-Alphen effect, exactly how we expected from our theoretic theory. Okay, so I could list more examples. However, in the interest of time, I will stop here because I want to come to a more interesting point. So there's several examples of theories where authors correctly identify new frequencies as combination frequencies. However, there could also be materials where somebody observed quantum oscillations and by mistake identified them as hallmark of a Fermi surface, even though there is no Fermi surface present, or at least not for this orbit. But it's very hard to make a claim here because usually the experimentalists know their data better than we do. However, I believe that this could have been already observed is a iron-based superconductor. So I think we always get back to iron-based superconductors in the last talk, and I will also do that. So iron-based, so I will look at iron selenide. Iron selenide is believed to be a high TC superconductor with S plus minus wave. Now, before you fall into the superconducting phase in iron selenide, you observe some sort of nematic phase. So you break rotation symmetry without breaking translation symmetry. Now, two quantum oscillations measurements show that in this nematic phase, you can actually observe a new quantum oscillation frequency which emerges from the lower end of the spectrum. This is this lambda frequency here. which comes basically from below as soon as you go into the nematic phase. And what I want to propose is that actually this frequency lambda is not a does not come from a Lifshitz transition, so not from a new Fermi surface which arises, but it's just generated by quantum oscillations of the quasi-particle lifetime, so it's a combination frequency. Now, in order to explain how this could work, I need to show you the Fermi surface of iron selenide, which is on the right-hand side. So we have 4 pockets. There's electron pockets here and here around the corners of the, or like the edges of the Brillouin zone. And there's hole pockets here around the gamma point. Now, for what I want to tell you, it's sufficient to focus first on the electron pockets. So that's the reason I drew a simpler Fermi surface here. And this model has a symmetry, which is a C4 rotation symmetry. So if you rotate by 90 degrees, everything is the same. Now, so what we did is we implemented that as a minimal model numerically. We introduced a magnetic field by introducing a Peierls phase. We put in impurities, which couple these two Fermi surfaces, and then computed conductance numerically. What you then can see is one single quantum oscillation frequency. Why only one? Well, there's 2 Fermi surfaces, but they're exactly degenerate, so the difference is 0, and you only get 1 quantum oscillation frequency. Now, what happens if you go into the nematic phase? So this is schematically what happens in the nematic phase. One of your pockets spontaneously grows, whereas the other one spontaneously shrinks. Now then, of course, you can directly see this in your quantum oscillation experiment or in our numerics, because the frequency just splits up. So here the frequency is double degenerate because of the 2 orbits. Now one orbit grows, the other one shrinks, and you can see 2 quantum oscillation frequencies here. But additionally, due to the impurities which couple these 2 electron pockets, you can see another frequency here at the lower end of the spectrum, which looks very similar to what people observe in iron selenide here. So this is the experiment in the inset. Okay, so now, if there is interband coupling here between these 2 electron pockets, there's definitely going to be a frequency which looks like that. The only question is now, like, is there a possible mechanism which would generate this sort of interband coupling between our electron pockets? So first, I want to say that, so what sort of coupling is, I want a coupling between these 2 pockets, because these are the electron pockets. What I don't want, because it's not observed in experiment, is a coupling between the pockets at gamma and these beta pockets. Now, this is actually in accordance with the believed S plus minus superconductivity, because impurity transitions between the 2 electron pockets are not pair breaking, whereas the other ones would be pair breaking. But still, that doesn't give us a mechanism. So what could be a possible mechanism? So we are suggesting 2 of them, 2 possible ones. One of them is, you can basically see that here the beta pockets share the XY orbital character here, both of them. So if you have some sort of scattering, which is orbital selective in the sense of that it orbits a stronger scattering channel along the DXY orbital than on the other orbitals, then you directly get a sizable coupling between the 2 electron pockets. The other option is a little bit more involved. This is this here. So in fact, iron selenide has 2 iron atoms in its unit cell. So this is not the correct Brillouin zone I'm showing on the left-hand side, but this here is the correct Brillouin zone, the dashed black square. And then you can see that basically the 2 electron pockets fall on top of each other. So if you have only low momentum scattering, you would also get a sizable coupling only between the 2 electron pockets and not between the gamma and the electron pocket. Now, let me also mention at the end here that in principle, what we consider is impurity coupling, because it's very easy to do numerics then. But in principle, you can also get the same physics when you scatter on fluctuations. So our conclusion for iron selenide would be that there is no additional pocket in iron selenide, even though people observe an additional frequency in the quantum oscillation experiments. And actually, you can use that frequency very interestingly, because you can see here, this frequency builds up like an order parameter, and it actually provides direct access to the nematic order parameter. And it also nicely quantifies the interband coupling we have between electron pockets, and therefore allows you to learn something about the possible scattering mechanisms in iron selenide. With that, let me come to my summary. So quantum oscillations remain, this is too far. Quantum oscillations remain an established tool for measuring properties of metals. However, we have to be careful. Not every quantum oscillation frequency we can observe actually has an underlying semi-classical path, has an underlying Fermi surface. There are quantum oscillations of the quasi-particle lifetime, which can happen in your system just because of scattering. Nevertheless, these quantum oscillations of the quasi-particle lifetime allow you to determine additional properties of your material. You can use them to, for example, study the temperature dependence of your lifetime. You can quantify interband coupling, a property which is otherwise not really accessible in experiment. And you can, in iron selenide, you can directly access the nematic order parameter. So in the end, let me thank my collaborators. First, Johannes Knolle, who's my PhD advisor, and also the experimenters for CoSi, which are Nico Huber, Christian Pfleiderer, and Mark Wilder, who all did here amazing work. Thank you.